Good morning, everyone. My name is Deirdre Denman, and I'm the Marketing Coordinator at EandM. Thank you for attending our Learn in 30 webinar titled Sizing a General Purpose Drive. After the webinar, we'll be doing a short Q&A. Please type any questions or comments into the Q&A box, the chat box, or you can email us at webinars@eandm.com. I'd like to introduce your presenter for this morning, Melissa Jarama, Drives and Motion Product Specialist at EandM. Good morning, Melissa.
Good morning, Deirdre, and good morning, everyone. Thanks so much for joining. In this webinar, let's review a few key questions you should ask yourself when deciding on the best general purpose drive for your application. Let's say that you know the motor you will use, but what next? How can we pick the right drive, and what other components may be required? The considerations provided today will be generic and may not cover specific application or industry concerns, so please do not hesitate to ask questions in the chat, or as Deirdre mentioned, reach out after the webinar and we would be more than happy to help. Again, this will be a generic overview and it will not be specific to Siemens VFDs. However, some comments that I make and the photos of the VFDs that are shown will be the Siemens Dynamics G120 drive. So let's take a quick look at what we will cover today before jumping into VFD considerations. Let's first review the three motor control options that are available: contactors, soft starters, and then variable frequency drives. Then let's quickly touch upon the main benefits of utilizing a VFD over a contactor or a soft starter. And then I'd like to take a quick second to highlight a fantastic resource from Siemens called the Sinasave software, which can help you determine energy savings of a VFD in your application. And then once we are confident that a VFD is the best solution for us, we can review what we should consider when we're selecting our VFD system. So to run an induction motor, we need to provide power. So we have three options to provide this power to the motor. Your first and lowest cost option is an across-the-line contactor. It will provide 100% power to your motor, but does not provide inrush current protection. Inrush current is the maximum instantaneous input current that's drawn when an electrical device is first turned on. A negative of not having inrush current protection is your motor will receive full power at once. So you may notice a bit of jerking and mechanical shock at initial start, but once accelerated, you should run at full motor speed smoothly. But one main deterrent to not having this inrush protection, that is, if your motor sees too large of a current, it could be damaged. So if you need this inrush current protection, or if you would like to start the motor smoother than your across-the-line contactor, you should consider a soft starter. You receive a smoother acceleration and the motor runs at full speed smoothly. One negative is that you cannot vary your speed. You can only accelerate and run at full speed. So your third option is the variable frequency drive, VFD or drive, as I'll continuously call it different things through this webinar. A VFD is the only option that's going to protect against inrush current, provide smooth acceleration, and it will also allow you to vary and accurately control your motor's speed and direction. Being able to control your motor speed has significant benefits. The first is reduced energy consumption. If you are not running your motor at full speed, you are not applying the maximum power to the motor. With this reduced energy consumption, you can significantly lower your operational costs. We'll take a look at this on the next slide when I describe the Sinasave calculator. Aside from energy savings, another way a VFD can help with costs is through tight process control. When you have better control of your motor speed, you can optimize your process, make fewer mistakes, and increase your throughput. When we do not have the jerk from inrush current, you can reduce the wear and shock and increase the life of all your external components to the motor. You can also eliminate the need for extra components in your system. Say you have a few different motors that need to run at different speeds. If you utilize a contactor or a soft start, that motor will only output the rated speed, so you may need to use some gearboxes or other components to make sure that you get the output speed you need. A VFD could eliminate the need for these gearboxes or other external components and can control the motor at the correct speed. In addition to eliminating the need for external components like gearboxes, a VFD also has a built-in voltmeter, ammeter, wattmeter, frequency meter, and temperature meter, so there's no need for these external measuring components. Now, to get real numbers for the energy savings a drive can provide, you can utilize Siemens Sinasave software. This free software lets you select different motors, contactors, soft starters, and drives, and compare how they would operate in your system. You can compare possible energy savings along with total cost of ownership to see if a product is going to be the right fit for you. When you visit sinasave.siemens.com, you have 3 options to select from. Do you have a pump system, a fan system, or another type of motor system? Once you make this selection, you're asked about the products you're interested in, say a soft start versus a VFD, and then specifics about your application. What is your flow rate and operational time? Once you complete these questions, you can export a PDF that provides an overview of the comparison. And most importantly, at the end of the document, you receive information on total energy costs and amortization of the drive. So now that we have decided the VFD is the best choice for us, what's next? What should we ask? The first question is, what available power do I have to input into this drive? What are the voltage, frequency, and current values? It's important to consider the protective device that will be mounted in between your main power and your drive. All Siemens drives require a protective device, such as a fuse or circuit breaker, and it's important to make sure you consider the power restraints of this device when determining the power your drive will see. If your protective device is your power constraint, this device's output should be considered your input into the drive. Now that we have confirmed the input power into the drive, let's confirm the quality of this input power. Do you have dirty power or unexpected voltage distortion that could interfere with the drive and cost you extra operational costs? Could harmonics cause excessive current draw and overheating? And would you like to reduce the total harmonic distortion at the drive input? Or say, do you have to meet specific IEEE 519 harmonic distortion requirements? If you answer yes to any of those, a line reactor may be required. Each Siemens Dynamics drive offers line reactor recommendations in each installation manual and other recommendations for reducing harmonics. Some Siemens drives offer an integrated DC link designed in, which eliminates the need for an external reactor at all. So that was power into the drive. But how do we decide the power requirement out of the drive into the motor? Let's take a look at our motor nameplate. What is the voltage and the frequency that are listed? But most importantly, what is the motor nameplate FLA? It's extremely important to size your motor requirements off of the current requirement and not horsepower. Horsepower should only be used as a reference to a speed and a torque and not for the size of a motor in a drive. Let's take a look at this example here for how current can be different when the horsepower is the same. Here are 2 motors rated both at 5 horsepower. One is a 2-pole motor and the other is an 8-pole motor. The 2-pole motor has a much higher speed and a lower torque generation than the 8-pole motor. The current requirement on this motor nameplate is 5.9 amps. The 8-pole motor has a lower speed but generates more torque than the 2-pole motor. The current requirement on this motor nameplate is 7.9 amps. This extra torque generation requires an extra 2 full amps more. If your VFD is not rated for your full current requirement, you will not get the performance output that you need. And so this is describing continuous operations, but what about for startups and quick stops? For these starts and stops, we need to consider the drive's overload ratings. Do you have an application like a pump or fan that does not have significant acceleration requirements? Then the low overload or LO rating might be for you. But what about applications like elevators and storage and retrieval machines, where quick accelerations are crucial and a larger overload may be required? Then you want to utilize the high overload or HO overload. These are just some general examples of applications for these overloads, but ultimately it's important for you to determine what your acceleration requirement for your motor is, determine what the current draw will be, and make sure that the drive can output this current. The overloads above are specific to the G120, and every drive has its own overload value, so make sure to always double check when sizing your drive. Last note on overloads, if you're ever reviewing Dynamics drive material and an overload is not specified, it will be the LO or low overload. So that covers almost everything for the drive's input and output power considerations, but before we move on, let's make sure there are no other conditions that could negatively affect the rated power of the system that we have sized so far. Siemens drives are rated for specific ambient temperature, altitudes, and vibrations, along with other considerations such as output pulse frequencies. If you are operating outside of these ratings, it's important to review the installation manual for any power or current derating considerations. If these derates are not considered, you will not get the performance that you need. So we have sized the drive for the correct output power, but now how is this drive going to output the power to the motor? we need to choose a control mode: voltage, frequency, vector, or torque control. Voltage frequency control is just what it sounds like. If you change the voltage and frequency output to the motor's speed will change. This is the simplest type of control and is used for applications that need simple speed control without outside factors that could change the speed requirement. Examples are simple conveyor belts, pumps, fans, and compressors. There are a few different voltage frequency relationships you can have, and I'll explain that more on the next slide. With vector control, voltage and frequency are still manipulated to provide the correct output power, but now the rotor or motor output shaft is tracked via current and voltage measurements with or without encoder. This is used for applications that require precise speed control, especially for dynamic applications or where there are a lot of speed changes. Examples include more complex conveyor belts, hoisting gears, and cranes. You can use vector control with or without an encoder, and I will cover this a bit more right after we cover the voltage frequency modes. And last, torque control mode uses a similar method to vector control, but where vector control focuses on controlling speed, torque control is specific to torque. You typically use this control mode when the motor speed can be controlled, not by the drive output, but by an external factor. It is always used when torque is crucial, for example, a winding machine. While it is important to complete the winding or unwinding of a roll quickly, it is more important to make sure that the torque is precise so that there's the right amount of tension in this roll for the specific diameter. Just like vector control, this can be used with or without an encoder, and I'll cover this right after vector. So let's look at voltage frequency control. There are 5 different types of modes that you can use. Let's first look at linear applications like conveyor belts, compressors, or extruders. Linear mode is used when the voltage and frequency are proportional throughout the speed range. If there are load changes in your system, you may slow down as the load increases. If this is the case, then you may want to consider flux current control mode. This is similar to the linear mode, but it does adjust for minor load changes. In addition, this is a great mode for motors running at low speed. Now let's take applications considered nonlinear, where the load changes during startup, like a centrifugal pump or a radial or axial fan. These applications require that as you increase your speed towards the set point, you need more torque to get to that speed increase. This is when quadratic control mode is used to make sure that you have the most efficient ratio as your speed increases. In between linear, flux current control, and quadratic mode is economy or eco mode. If you have an application where you are always running at a constant speed after ramp up, this might be the most energy efficient control mode for you to use. And lastly, for voltage frequency control, we have multi-point or multi-programmable control mode. This is used for any type of application where you want to map your frequency speed range, or if there's a nuisance frequency causing you trouble that you want to skip. For example, this could be used for a mixing application when you notice that some frequencies create far more vibration and noise than others. You could use this mode to skip those high noise points. Next is vector control mode. Rather than deciding the voltage frequency relationship, vector mode will use algorithms to output power to the motor to control speed. If you accurately enter your motor data and tune your motor during startup, this can be the most accurate control mode. It can be more accurate of a control mode than voltage frequency for low dynamic applications. But what about dynamic applications with significant load changes, like variable load conveyors? That's when you might want to utilize a closed loop system and use encoder feedback and these algorithms to help you have a more dynamic speed control. And last, for vector control, we have position control, where in addition to speed needing to be precise, it needs to be applied in a specific location. Examples of this would be bottle capping or stamping machines. And now on to centralist torque control. This is very similar to vector control, but rather than using algorithms to determine the speed, we'll use algorithms to determine the torque. It is just like vector control, where it relies heavily on your entered motor data and the internal ID that you do during startup. And again, like with vector control, if you have more of a dynamic application and you need a closed loop system, you can use torque control with an encoder, and this can provide speed and torque control. Say you have an axial winder where you need to keep track of speed and tension. So now that we have figured out what our output power needs are and how we're going to control the output power to the motor, we should consider how far this power needs to travel to the motor. How long will your cables be from your drive to your motor? VFDs output a PWM or pulse width modulation wave, and in this wave there tends to be a production of noise and voltage spikes, which are amplified by longer cable lengths and the additional capacitance of those cables. A load reactor will provide increased inductance in your cable run and reduce the impact of these spikes, which will reduce the noise and also protect the motor from damage. Make sure to review the VFD manual for recommended cable lengths with or without this motor reactor. Next consideration, will you be using a VFD or an inverter-rated motor? These motors are designed with insulation and bearings to withstand the voltage spikes that the VFD outputs. If you do not have a VFD or inverted-rated motor, or if you just want to protect your motor for longer life, a DVDT filter can be used. These reduce the speed of the voltage spikes to the motor and allow non-VFD or inverted-rated motors to be operated with a VFD. Or could you use a sine wave filter instead? These are similar to a DVDT filter where there is a reduction in spikes, but it's also designed to clean up the PWM wave coming out of the drive to have it best resemble a true AC sine wave. This provides ultimate protection to the motor. So we've officially sized the drive through throughput considerations to the motor, but what about power that might come back to the drive from motor regeneration? Did you know that your motor turns into a generator when your load is pulling the motors and the drive is trying to stop it, such as when braking the motor? When this happens, regenerated power tries to return back to the drive. Do you expect this kind of power regeneration? If so, check and make sure that your drive of interest is designed to handle this regen. If not, a braking module and a braking resistor may be required. The braking module, also known as a braking chopper, is a switching device that controls when regenerated power is fed through the braking resistor. Some drives, like the Dynamics G120, have these modules built in, but others require one to be purchased separately. The braking resistor absorbs and dissipates the regenerated power before it can reach the drive. To make sure that you get an external braking resistor that is the correct size for the amount of regen that you expect, all Siemens drives have recommended braking resistors within each manual. And are you going to be utilizing a motor with a holding brake? If so, you are going to need a brake relay for your drive. If you have a standard application, a standard brake relay will suffice. This relay has two interfaces, a connection to the power module and a normally open contact to control the motor brake solenoid. If you have an application that has safe brake control considerations, such as an elevator or an application with another type of application with a hanging load, you will need a safety rated relay. This is like a standard relay, but it also has an incorporated 24 volts to monitor the brake control for short circuit and cable breakage. Now we've figured out all the power requirements for the drive. How are we going to tell the drive what to do? How is it receiving its commands? How many digital and analog inputs and outputs do we need? Is there enough for our application, or do we need an extension module? Does any of our I/O need to be safety rated? Will you be using the drive as a standalone system and only controlled by this I/O, or are you going to also utilize a PLC? If you're using a PLC, make sure that the drive has a compatible communication protocol. We always recommend avoiding protocol converters whenever possible. During diagnostics, it's best to only have one place to check and not multiple. So that was I/O and PLC communication, but how do we plan on communicating with the drive? Once the drive is installed in an operation, how will we review any faults that occur? Do we plan on a simple setup and just want to use an operator panel, or would we prefer to utilize software for a more detailed setup? Maybe we want to use both? If you're going to use an operator panel, do you plan to install it direct onto the drive, or would you prefer to access it without opening up your control panel? If the latter, Siemens can provide a door mounting kit, which will include cabinet cutting instructions and an IP54 seal so that you can use the panel on the cabinet door. But if you want to communicate with your drive and you don't want to be near the cabinet at all, perhaps you could use Siemens' new Smart Access module. It is designed to be used with your favorite tablet, computer, or cell phone and allows you to communicate with your drive without being near the cabinet or its flash arc barrier. And lastly, now that we know that we have the right power and that our drive will control our motor, let's make sure that it actually fits where it needs to go. Do we have an existing cabinet that this drive needs to fit into, or do we have a little leeway? Does our drive meet these constraints? In addition to physical dimensions, make sure to review the drive's manual for cooling space requirements. If the drive does not have proper air flow and cooling, it will not operate as rated. And then how do we plan to mount this drive? Will the drive be mounted and enclosed in a cabinet, or could we utilize a push-through design where the heat sink of the power module is actually pushed outside the cabinet, which can reduce cabinet space and possibly the need for an AC system within the cabinet? Whatever your decision is, make sure to confirm what mounting accessories you need during your selection process. And just one last consideration I ask is for you to look into the safety that Siemens offers integrated into the drive. A lot of safety can be used without a PLC, and why not take advantage of it? There's basic and extended functions available for general purpose drives, and let's just take a quick look at what's available. In basic functions, the first is safe torque off, which can be used with any application. Say we have an e-stop, and that e-stop is engaged, and once our motor has stopped due to the natural friction of the system, safe torque off will make sure that the drive does not provide any more power to that motor again until a manual reset. Just make sure that there is no unexpected movement during an emergency stop. STO does not help stop the motor, it only stops power from reaching the motor after the motor has stopped. If after your e-stop is engaged, you want to make sure that your application stops immediately, you would utilize Safe Stop 1. Safe Stop 1 will provide a counterforce to the motor to help stop it in the time you require. Once stopped, Safe Torque Off will make sure that the motor does not restart again without a manual reset. And as mentioned with the Safe Brake Relay, the drive can implement safe brake control for applications that have hanging loads. And it will safely control and monitor the brake in a de-energized state. Now on to the extended functions. Say you have an application where too slow of a speed can cause person or product damage. Safe Speed Monitor is a function within the drive that will send a safe signal when a speed is below a given threshold, and you can decide what to do with this signal. For example, a mixer mixing cement starts to harden the product and a tool is spinning too slow. The drive can let your PLC know, and the PLC can alert someone and try to assist to salvage the product. Or say there's an application where slow speed means that something is inconsistent and you don't want someone to enter the area just in case. The drive could send the signal to a PLC, and the PLC could lock a door, not allowing anyone to enter. Then there is Safe Limited Speed, which is the opposite, and it tracks of when you are exceeding speed. In applications such as winders and punches, when too fast of a speed could damage people and product, this can be used. When this is activated, the drive will monitor the speed, and when it sees that it's increasing too much, it will try to get the motor back to the correct speed. If it cannot, it will implement either a coasting stop with just Safe Torque Off or the defined time with Safe Stop 1. And lastly, there is Safe Direction Control, which does exactly what it sounds like. Say you have an application with a saw blade. You probably only want that saw blade to spin in one direction. With Safe Direction activated, the drive monitors which way your motor is spinning. If it starts to spin in the wrong way, the drive will implement your choice of either a coasting stop or with Safe Torque Off, or a defined time stop with Safe Stop 1. One last point about safety is if you are going to use extended functions, make sure that you get your extended safety license for each axis. And so those are all the questions I could think of for you to consider when sizing a general purpose drive without getting into too many application specifics. If there's any key questions that I've missed, I'd like to open up the floor now to see what we can answer.
Thanks, Melissa. So yeah, we would like to open it up for a couple of questions. Please type any questions you have into the chat box or Q&A box, or you can email us at webinars@eandm.com. We did receive one question during the presentation. So does Siemens offer any tools to help size a general purpose drive?
Absolutely. You can check out the DT configurator or drive technology configurator, and it will ask you step-by-step questions to help you get a recommended drive, or myself or anyone at Siemens would be happy to help as well.
Okay. Let's see. And I think that's it for the questions.
Awesome. Thanks.
So that concludes our Q&A portion of the webinar. Thank you, Melissa, and everyone who attended today. If you would like to review any portion of this webinar, a recording will be available on our YouTube channel and on our website at EandM.com. We'll also send you the presentation via email on Monday for you to watch again. We hope to have you again next Friday for our Learn in 30 on Profinet push buttons. You can register for that webinar on our website at EandM.com. Thank you so much.